talk about bonding, I believe. And really, there's two types of bonding we're talking about in this chapter, and we focus mainly on most of the time last time on ionic bonding. And as we talked about, that is always between a metal and a non-metal. And because of those periodic trends that we talked about as well last time, what we always will see in this situation is the metal has all of those trends, which pretty much wants to give away its electrons, not really hang on to its electrons. So we will see a transfer of electrons from the metal to the non-metal. And that's because, as we also talked about with all those periodic trends, non-metals pretty much have all the opposite sort of trends, which is like they like to hold on to their electrons. They also like other people's electrons. So they really are the ones that want to gain electrons. And as a result of that, as we talked about, we will form our cation, which is positively charged as a result of those loss of electrons. We will form our anion as a result of gaining those electrons. And once again, one of the main things about an ionic bond, as we talked about, is there is absolutely no sharing of electrons in this situation. So we have no sharing of electrons. It is that electrostatic attraction between the positive and negative ions that holds it together. And that's different than what we see in covalent bonding. And with covalent bonding, that typically is between two nonmetals. And again, because really those nonmetals are pretty much in the same location on the periodic table, they also will have very similar sort of periodic trends in terms of what they want to do with their electrons, and pretty much they both want to hang on to their electrons. They also both want to kind of gain electrons. So instead of a transfer of electrons like we see in ionic compounds in a covalent bond, we actually see sharing of electrons is sort of what will happen in this situation, because again, they both really want to hang on to their electrons and not really give them away. And as we will talk about today and in the rest of this chapter, again, that sharing could be equal or unequal sharing of electrons, but in a covalent bond, there is some aspect of sharing that is happening between them. So we talked about using Lewis dot symbols or electron dot symbols to represent sort of bonding, and we use Lewis dot symbols, or just generically called electron dot symbols, which is basically the symbol and one dot for each of the valence electrons that it might have. A reminder that, again, the group number on the periodic table equals the number of valence electrons that an element has for the representative elements, which means you don't really necessarily have to write your electron configuration to figure it out. You can just go to the periodic table and get the group number. So we looked at sort of the formation of bonds like our sodium, which is group 1, which has its one valence electron, being our 1s2, 2s2, 2p6, 3s1 being that electron right there, which is its valence electron. And we took something like fluorine, I think, which had 7 valence electron, which is group number 7, as 1s2, 2s2, 2p5, this being the 7 valence electrons that there are. Remember that when we use Lewis dot symbols to represent ionic bonding, we do want to show the transfer of electrons from the metal to the non-metal. The result of that is our metal will lose the electron and will make a positive charge, which, as we talked about, you do need to include the charges when you draw an ionic sort of bond formation. The fluorine will pick up that electron and will gain a negative charge. And once again, that positive negative charge is what holds that together. The main purpose of all bonding, as we talked about, is pretty much for everybody to achieve noble gas configuration. And basically, by sodium losing that valence electron, it drops down to 10 electrons, which means it has the same electron configuration as neon when it has a +1 charge. The fluorine has a spot, as we talked about, for that electron, so it's going to fill in there, and that will fill up actually the p subshell in that case, and that will give it also, in this case, 10 electrons, which will move it forward to neon's configuration. So in the case of ionic bonds, the way that everybody's able to achieve noble gas configuration is by gaining and losing electrons. Metals will go backwards on the periodic table to the noble gas, which is group number 8 on the periodic table. That comes right before them. And non-metals will basically gain those electrons and go forward on the periodic table to the noble gas that comes after them. As we also saw, I think when we looked at like calcium fluoride, again, in some cases, you need more than one sort of element. For example, again, in that situation, we needed 2 fluorines to make sure that calcium could lose both of its electrons. And again, as we talked about, that's why when we put a positive ion, negative ion together, overall 0 charge is really so that everybody can get to that noble gas configuration. The other important thing in terms of bonding, as we were talking about as well, is our friend hydrogen. Again, on the periodic table, it is helium that is past hydrogen. So hydrogen should only have 2 in any type of situation. We finished up sort of talking about covalent bonding. And when we think about covalent bonding, like we talked about with the hydrogen, when 2 hydrogen atoms come together, they have identical periodic trends. So they are definitely going to share the electrons, which can be represented with either a line or 2 dots between the 2, where each of those electrons represent or count for each of the atoms that are present. So here in this case, our hydrogen gets 2 electrons on both, which gets it to helium, which makes it happy. We also looked at fluorine, I think, as well. And again, when fluorine comes together, we get those electrons being shared between the 2 fluorines, which again can be represented as either dots all the way around or dots and lines. Again, those fluorine in the middle, there's electrons in the middle, it can account for both. So that gives that fluorine on the right 8, gives this guy on the right 8. And again, 8 is again a magical number in bonding, as it will mean you pretty much have the same electron configuration as the noble gases, right, which have 8 valence electrons in it. We also talked about the names of these, right? These guys are not involved in bonding are what are referred to as lone pairs, are non-bonding electrons. And the ones involved in bonding are what are referred to as bonding electrons. Any questions on any of that stuff I think we talked about last time there? All right, so then let's continue on here. So again, a Lewis structure is a representation of covalent bonding. As we talked about, we do only show the valence electrons in Lewis structures, and that is because those are the ones that are involved in bonding. Those are the ones that are furthest away from the nucleus, not held as tightly, right, because of the effective nuclear charge, and they're able to be sort of removed much easier. Remember, all these elements still have their core electrons, which are closer to the nucleus and not really involved in bonding, but obviously they're still there when we do it. When you draw your Lewis structures as well, as we talked about, you want to always make sure you include both the non-bonding electrons and the bonding electrons. So if we look at water, in this particular case, the oxygen, by sharing electrons with both hydrogens, is able to achieve 8 electrons. And again, each of the hydrogens here able to achieve 2 electrons, which makes everybody happy, just like what we see with our fluorine, everybody able to get to that sort of octet rule or noble gas sort of configuration. So speaking officially about that rule, that is the octet rule. And that's the rule typically that we follow when we're drawing Lewis structures. And basically the rule says that everybody will continue to make bonds until they pretty much have 8 electrons around them. Obviously the main exception being hydrogen, which should only have 2 electrons around it or next to it. And that's what's sometimes referred to as the duet rule, which means it has only 2. So as I mentioned before, pretty much when you draw Lewis structures that have hydrogen, that's pretty much what hydrogen should always look like. Yeah, it's just a line to the hydrogen. Hydrogen should not have any dots around it. Once again, hydrogen should never look anything like this, dots and like a triple bond, because it makes it look more chemistry-like. Otherwise, you get a big X like that. So don't do that. Again, it's a common mistake. People just like throwing things on there on the hydrogens. That also means that we will never really find hydrogen in the center position in a molecule, right? Because if it's in the center position, it will have obviously more than 2 electrons, right? So it's always on the outside, always a single bond on the outside, and that is always how you'll find your hydrogen. Now, we touched upon this a little bit last time, but officially here, there are obviously single bonds, double bonds, and triple bonds when we draw it. So in a single bond, like we see here with fluorine, it can be represented by one line. Again, our 2 dots of electrons are a pair of electrons. And in some cases, in order to reach the octet rule, that's pretty much all you need. You could just single bond up everybody and everybody will be fine. In other cases, it sometimes requires double bonds to do that. And in the case like a CO2 here, we could see the carbon, by sharing electrons with both oxygens, ends up with 8. And the same thing with those oxygens, by sharing with the carbons, will also end up with 8 electrons. And actually, we need 2 double bonds in the case of CO2 to be happy. And again, a double bond represented by 2 lines, which represents 2 pairs of electrons, are 4 total electrons when we look at it. Now, in certain cases, double bonds are not going to sort of cut it. They will actually need a triple bond to meet the octet rule. And something like nitrogen, for example, is an example of something that will actually need a triple bond to reach the octet rule. And that means it will have 3 lines, or again, 3 pairs of electrons, or 6 total. Also carbon down here, by sharing with the hydrogens and also sharing with the other carbon. Each of these carbons are able to achieve basically 8 electrons. And once again, our hydrogens here able to share and achieve 2 electrons in this case. So we're going to talk about the proper sort of order as to how you draw Lewis structures sort of correctly. But one common mistake that people make is they want to like double bond and triple bond like right out of the box, and just kind of keep throwing bonds in as they draw Lewis structures. And you typically, in a lot of cases, probably don't want to do that. Usually you want to kind of reserve a double bond or a triple bond for a situation really where maybe the octet rule isn't met, and then you would want to kind of try to fix it by making a double bond or a triple bond. Usually double bonding, triple bonding out of the box, usually not the best move when you're drawing Lewis structures. So when we talk about sharing of electrons, there is one thing that really sort of determines how those electrons are going to be shared between each. This is what is sometimes referred to as, we're sort of talking. And bond polarity is different than molecular polarity, which is the whole molecule as a whole in most cases. So what kind of helps us determine whether or not we would expect electrons to be shared equally or unequally is actually electronegativity. So as we talked about electronegativity, the ability of an atom to bring electrons towards itself. So for example, when we take our hydrogen, in this case, and we put it together with our other hydrogen, we are going to get that sharing of electrons, and we're going to get that bond formation. But in this situation, because obviously they are both hydrogen, what we would expect to happen if we think about sort of the electrons in these bonds, we would kind of expect sort of a nice equal distribution of those electrons between those 2 atoms, because frankly, it's like pulling on a rope. You got like hydrogen pulling this way and hydrogen pulling this way, and it's kind of the same pull in both directions. So we're going to get a nice equal sort of pull on those electrons, and we're going to end up with actually equal sharing of electrons here. So we'll end up with equal sharing of electrons. And in a situation where we have equal sharing of electrons, this is what is sometimes referred to as a nonpolar covalent bond. Most people kind of leave the covalent part out of it and just call it a nonpolar bond. but it is still a covalent bond. It is sharing of electrons. It is equal sharing of electrons. Again, the positive from the hydrogen, the positive from the other hydrogen, going to pull those negatively charged electrons equally between the two. And we have really nice sort of even distribution over everybody. And you could kind of think of this type of bond, because there's really equal distribution of those electrons, as kind of being like a neutral bond in a sense. You know, there's not going to be a side that's more positive, not a side that's more negative. Nice equal kind of distribution of our electrons over the entire bond. So when we take something, for example, though, that is different, and we take something like hydrogen and fluorine in this case, if we take something like hydrogen and fluorine, when we put it together, first off, we do know that when we talked about electronegativity on the periodic table, electronegativity increases, right, as you go up and to the right, and decreases as you go down. The most electronegative element is actually fluorine. So when we put hydrogen together with fluorine, we're no longer going to actually end up with equal sharing of electrons. And that is because the fluorine molecule, or the fluorine atom, will have a much stronger pull of those electrons, right? So those electrons, if my yellow here is the electron density, it's going to have a much greater sort of pull of those electrons towards the fluorine side of the bond. And that's going to create something that's a little bit different than what we see when we had something like our H2 or even our F2. And we're going to create what is referred to as a polar covalent bond, or just a polar bond. And that is a result of unequal sharing of electrons. So unequal sharing of electrons is a polar covalent bond, or most people just call it a polar bond. The other sort of consequence of this is, if all of the electrons are kind of hanging out towards the fluorine versus the hydrogen, it is going to create some charges within that bond. And the fluorine side should be more positive or more negative? The electrons are hanging out by the fluorine, it should be more negative. So what happens, because those electrons are hanging out towards the fluorine side, it creates a partially negative charge on the fluorine. That's a delta symbol. So that's a delta negative or partial negative charge. And because the electrons are kind of heading towards the fluorine on the hydrogen side of the bond, it creates a partially positive side to that bond, which can be represented by those two symbols. We also can use what is sometimes referred to as a dipole arrow, where we point the arrow towards the side that's more negative. So it always points to the side more negative, and the back end of the arrow, which actually makes like a plus sign, creatively enough, is the side that's more positive. So that is what is referred to as a bond dipole arrow. We draw them only for bonds where we have unequal sharing of electrons, and it is a polar bond between them. Any questions on that there? Now, why is it in this case only a partially positive charge and a partially negative charge rather than a full positive charge and a full negative charge? Why is that? That's absolutely right. So this is still a covalent bond. So even though they are not sharing those electrons equally, there are still some aspect of sharing that's happening there, which is why it's partially negative on one side and partially positive on the other side. And that's different than what we see in an ionic bond, where there's absolutely no sharing of electrons. We have a full transfer of electrons from one to the next. And that's why we get a full like positive charge and a full negative charge and make ions in that case. Here we don't make ions because they're still hanging on a little bit. Yeah, so that hydrogen is still hanging on a little bit to those electrons. They haven't fully jumped the shark there to the fluorine side, and they're still kind of hanging in there. So that's why we have partially positive, partially negative charges. And that's a really big effect on properties of certain molecules. If they have this type of bond in there, it gives them some different properties, as we'll talk about in later chapters. Other questions on that? There's my smear of positive charge. So we could think of a polar bond as sort of an intermediate between an ionic bond and a nonpolar bond. So to summarize sort of the three different types of bonding that we talked about so far, on one end of the spectrum, we have our ionic bond, where it is a metal and a non-metal, where we're going to get that transfer of electrons, creating our cation, which is positively charged, and our anion, which is negatively charged. And again, it is that electrostatic attraction, no sharing of electrons. So something like sodium chloride is obviously an example of that. That's a sodium ion. And a chloride ion, as we talked about, pretty much if you see a metal and non-metal, no thought required, it's an ionic bond. Yeah, so that is basically what's going to happen. On the other end of the extreme, we sort of have a nonpolar covalent bond, or just a nonpolar bond. And that is between two nonmetals. And that is going to result in equal sharing of electrons, like our F2, our H2 that we looked at as well. And in the middle of these two is really what we were just talking about, which is our polar covalent bond, which is also between two nonmetals. It is also sharing of electrons, but it is unequal sharing of electrons in this case. And that would be obviously our example here, which is HF that we talked about. And again, creating those partially positive charges, partially negative charges, because there's still some aspect of sharing. Now, again, like I said, most people just call it a polar bond or a nonpolar bond, and they both are covalent bonds, which means they're both sharing electrons that are happening in that situation. I will say we'll see it in a couple of spots, but when you have something like these two here, which are nonpolar bonds, that is probably as perfect of sharing as you could get, because they're both the same element, basically. So they're both going to have the same pull on those electrons. So sometimes people will refer to this as a nonpolar bond most of the time, but some books and some people will sometimes refer to these guys as pure covalent bond. And a pure covalent bond is still a nonpolar bond, but it's just basically implying that's like nice and perfect equal sharing as you could get. As we will talk about, there's degrees of equal sharing. So there are degrees of really not equal sharing, but it's considered close enough to be equal sharing that's nonpolar. And there's sort of a cutoff as to where, all right, this is a little too much of not equal sharing. It's now going to kind of flip into a polar bond. So when we look at sort of electronegativity values here in just a second, we will see that difference that, we can have a difference where it's like perfect equal sharing. And then we could have a difference where not technically perfect equal sharing, but close enough to be called equal sharing and stuff like that. Any questions on any of those three different types of bonding there? So what helps us really figure out how things are going to be shared, as I mentioned, is really electronegativity, which again is that ability of an atom to bring electrons towards itself. And as we talked about, again, our fluorine there, upper right of the periodic table, the most electronegative element you could have. As we also talked about, if you go up to the right, there's not much past it on the right there, except for our noble gases, which again are perfectly fine the way they are. They're not really looking to do much. So that is why, again, we kind of cut off the electronegativity up there around fluorine. Electronegativity is related to electron affinity and ionization energy. And again, electron affinity is that energy change that occurs when somebody gains an electron. Ionization energy is the energy required to remove an electron. And again, on the periodic table, what we see for electron affinity is it increases as you go that way and decreases as you go that way. For ionization energy, same sort of trend, increases up to the right and decreases as you go down, right? And that's again why our nonmetals hang on to their electrons, and our metals on the left-hand side of the periodic table will release their electrons. So there actually is a scale that was sort of made by a guy named Pauling, and he came up with a scale for electronegativity that we can use to help us decide whether or not a bond will be polar or nonpolar. You could use it to help you figure out ionic, but you really don't need it because it's metal and nonmetal is all you need to know, but you can also do it for that. And Pauling's scale runs from 0 to 4, and Pauling did a lot of things. He also came up with the first model of DNA. Wasn't so right, but he came up with it. It wasn't too bad. But he was very big on megadosing vitamin C. You ever heard that? That was like him. He was very big on that. So when we have values for all these elements of 0 to 4, 4 is the most electronegative you could have. And 0, not so much. Yeah. So not very much at all electronegative, not really interested in bringing electrons towards itself. So we can use what is sometimes referred to as the change in electronegativity values, which is what the delta En stands for, delta change, En electronegativity. We could use the change in electronegativity values within a bond. So this is what we're use electronegativity for in most cases, is again what is referred to as bond polarity. And in most cases, and there are certain cases where it will also tell you molecular polarity, but in most of the time, we use the difference in electronegativity to help us determine what is referred to as bond polarity. And simply put, it just basically means between these two atoms, based on electronegativity values, do we expect electrons to be shared equally or unequally? It's basically what we would use this for. And in a lot of cases, especially when you have 3 or more atoms involved, it doesn't really tell you too much in a sense about molecular polarity, the molecule as a whole, but it will tell you between these two things how those electrons will be shared. Now, if we take the difference in electronegativity values, and it's a very simple process, you just subtract the two numbers that you find on the table, and you do it so you get a positive number. So you can just take the larger number minus the smaller number. If you take the difference in electronegativity, you get anywhere between 0 to 0.4. This is basically considered a nonpolar bond, basically equal sharing of electrons in this situation. If you are just above 0.4 to below 2, and your difference when you subtract the two numbers, that is some type of polar bond, which means unequal sharing of electrons are happening in this situation. And typically speaking, but not in 100% of the time. But if you're above 2, you probably got some type of ionic bond happening. And you can think about it, you know, get above 2, somebody on the right-hand side, somebody on the left-hand side are going to have very difference in electronegativity values. It's going to create that big difference. Once again, personally speaking, you don't really even need that because, again, metal, non-metal, put ionic, you'll be good in pretty much all cases. But you can typically go above 2. But there are certain cases where you will have an ionic bond that actually has a difference of a little less than 2. So again, it works in a lot of cases for the ionic, but not 100% of the time. So that's why just the metal, non-metal is the better thing to remember for that. Now, earlier we were just talking about the idea that if we have two things that are the same, right, they would have the same electronegativity value, right? Which means when you subtract those numbers, you should get the number of 0, right? So if you do sort of that difference in electronegativity and you get a 0, it is still a nonpolar bond, but this is the ones that sometimes are referred to as a pure covalent bond. When you have that sort of difference in electronegativity, that is 0, going to give you that perfect equal sharing. Any questions on that there? So let's take a look here. Obviously, that's our trend in electronegativity that we talked about. So here's a table of electronegativity values. So for example, let's take a look at the 3 that we just talked about when we talked about the 3 different types of bonding. We had our sodium chloride, right? We had our HF. And we'll do F2. Why not? We'll do these guys. Okay, so if we start with our sodium chloride, we would find sodium's electronegativity value there, which is 0.9. So that is 0.9. And chlorine, which is over here, is 3 on the right there, which is 3. So if we were to calculate the difference in electronegativity values, we're going to take 3.0 minus 0.9. I'm going to try it without the calculator. I'm going to go with 2.1 and hope that's right. 2.1 is above 2, which means based on our scale, we would expect this to be ionic. And once again, we really don't need that because we should know that's a metal and a non-metal, so it should be ionic. And again, you may not always get a difference that is that two chains. So for example, if you just let's see here. We did something like lithium bromide, for example. Lithium is 1, bromine is 2.8. So when you subtract that, that's a 1.8 difference. It's obviously not 2. So again, it doesn't work in every case for ionic. So again, that metal, non-metal is what you want to look at. We look at our fluorine and fluorine here. Fluorine is the most electronegative. As you can see, it actually has a value of 4 up there in the corner. And that would give us 4 for this fluorine and 4 for this fluorine, which means when we take our difference in electronegativity, 4 minus 4 is 0. And that definitely will fall under the non-polar bond, which is what we expect to sort of occur. And lastly here, if we look at our HF, we got our hydrogen, which is 2.1. We have our fluorine, which is 4. So we take a difference in electronegativity here, going to take 4 minus 2.1, 1.9. 1.9 is below 2, and it's above 0.4, which means that this is going to be a polar bond. Also gives you a little sort of hint of how unequal these guys are being shared. That is as close, almost as close to our ionic cutoff, right, of 2 or higher. So they are definitely being shared very unequally. So there are different degrees of sort of unequal sharing, if you will. There are some where it's really unequal sharing, and there's some where it's just a little bit of unequal sharing that's going to occur. Any questions on that there? So once you do some here, decide whether it is ionic, polar, or non-polar. And we give you a few here to do. Let's do the bond between carbon and hydrogen, the bond between nitrogen and oxygen, the bond between sulfur and oxygen, the bond between carbon and sulfur, the bond between potassium and chlorine. All right, so take a couple minutes to calculate the difference in electronegativity. Here's the scale, the carbon-hydrogen bond there. So our carbon value is 2.5. Our hydrogen is 2.1. So when we do the difference in electronegativity, that is 2.5 minus 2.1, which gives us a 0.4, which means this is considered a nonpolar bond. And really the reason for the cutoff is pretty much all organic molecules contain those bonds and they're nonpolar. So is this perfect equal sharing of electrons? It's not. It's kind of hedging a little bit towards the carbon in this case, right? But it's not enough to be considered a polar bond, unequal sharing of electrons. So this is what I was talking about earlier. There's some degree of difference in sort of equal sharing, but it's still considered basically an equal sharing of electrons. We look at our nitrogen oxygen here, nitrogen being 3, our oxygen there being 3.5. Our difference in electronegativity in this case, 3.5 minus 3, going to give us 0.5. And that 0.5 is above 0.4, which is our nonpolar cutoff, which means we would expect this to be a polar bond, the more electronegative atom would be the oxygen, right? And the more negative side of the bond would be heading towards the oxygen, right? So we could draw that arrow pointing towards the oxygen, which would imply that is going to have the partially negative charge on it. And obviously our nitrogen would be more positive in this case. Looking at our sulfur oxygen bond, our sulfur 2.5, our oxygen here 3.5. So our change in electronegativity going to be 3.5 minus 2.5, going to give us a difference of 1, which again is above 0.4, which means we would expect this to be a polar bond. Again, more negative side of the buffer. And was it potassium and chlorine? Thank you. All right. So and earlier we had our nitrogen, oxygen, our sulfur and oxygen, and our carbon, hydrogen. All right. So polar, polar, non-polar. Looking at our carbon, sulfur here, again, our carbon 2.5, our sulfur is 2.5, which means our difference in electronegativity is going to be 0 in this case. That means that bond is actually going to be non-polar, right? So this is a really good example that you can have two different elements that actually can be nonpolar. If you have two elements that are the same in a bond, it definitely is going to be nonpolar, but it actually can be nonpolar having that one. The reason for that is where they sit on the periodic table. That is carbon, that is sulfur. They are where sometimes referred to as the diagonal relationship to each other on the periodic table. One is further up and one's further to the right, and they kind of cancel out their differences and they end up the same. There's a few places where you see that when you look at the periodic table and this sort of relationship. Again, we see something like here and here. You also see it nitrogen and chlorine as well. You see it in that sort of diagonal relationship. So depending on where they are, they're just kind of not directly diagonal, but kind of diagonal and over one from each other. They may actually have the same sort of electronegativity values. Looking at our potassium here, which is 0.8, and our chlorine, which is 3. Going to give us our difference in electronegativity of 3 minus 0.8, a little 2.2 action, and that is going to be ionic. But once again, we have a metal and a non-metal, which means we should know it is ionic to begin with. Yeah. It would be, because the sharing there again is going to be basically equal. And that's basically what a sort of a pure covalent bond means. It's really sort of a difference in electronegativity where it's going to be basically 0. So you got literally the perfect equal sharing of electrons, which happens to be in this case 2 different elements, but they have basically identical sort of electronegativity sort of attributes. Other questions? Okay, so you would be provided obviously the numbers in some form, but you do need to know how to use it, obviously. Now, do you always need the numbers, and should you feel sad if you don't have the numbers, and what are you supposed to do with your bonding and all that? Where the answer is, in a lot of cases, you could use the general trend in electronegativity to help you make a fairly good guess as to whether or not the bond would be polar or non-polar. For example, we did nitrogen and oxygen. And if I did not have the numbers in front of me, I know that nitrogen and oxygen are in the same row on the periodic table. And if they're on the same row in the periodic table, electronegativity increases as you go to the right. And that would most likely be a polar bond because they're in the same row. And I would also make a pretty educated guess that it is the oxygen that should be more electronegative because, again, it is sitting further to the right. So even without the numbers, based on where they're sitting on the periodic table, you can make a fairly good assumption that that should be a polar bond. Now, if we look at another one that we looked at, which was our sulfur and oxygen here. Our sulfur and oxygen actually sit in the same group here on the periodic table. And what we know about electronegativity trend is as you go up a group, it increases. So once again here, because they're sitting basically on top of each other on the periodic table, we can make a pretty educated guess that it's going to result in a polar bond. And once again here, the oxygen should be more electronegative. So in a lot of cases, even if you don't have the electronegativity value numbers given to you, you could kind of use the general trend, especially if they're in the same row or if they're in the same group on the periodic table. You really don't need the numbers. You could probably make a fairly educated guess as if they are in the same row or in the same group, you're going to have a polar bond. And again, the one further to the right in the same row or the one further up in the same group would be the more electronegative one, the more negative side of the bond. Any questions on that? So once again, what we are looking at here is what is considered in most cases bond polarity. And all we are simply doing in most cases, we are simply looking at the two atoms that are involved in that bond and determining whether or not that particular bond is going to be polar or non-polar. It does not necessarily translate to molecular polarity, which is the polarity of the entire molecule. There's only one place where both electronegativity values, bond polarity, and molecular polarity are pretty much the same. And it is in a situation where we've seen actually up to this point, if we took something like HF or something like F2, we know based on our little guys here that this is our, again, our 2.1 and our 4, which means our change in electronegativity going to be our 4 minus that, which is 1.9, and then obviously our 4 and our 4, which had our change in electronegativity basically being 0. So we know the guy on the left, there's a polar bond. So bond polarity would be looking like that. We would have a non-polar bond on the right-hand side. By the way, do I draw the arrow for a non-polar bond? We don't. The arrow, again, is only for polar bonds. So both of these molecules are diatomic molecules, which means if we wanted to know the molecular polarity, which is the polarity of the entire molecule, not just between the two bonds or the two atoms in that bond, we could actually figure it out based on bond polarity, because how many bonds does each of those molecules have? Each molecule only has one bond, right? So in the case of HF, because it only has one bond in the entire molecule, and that bond is a polar bond, then that molecule should be polar as well. So the molecule itself in this case would be polar molecule, because the one and only bond in it is polar. Similar over here, this guy has one and only one bond in the entire molecule, and we know that that bond is a non-polar bond, which means by default the molecule here also has to be non-polar. So this is really the only place where bond polarity and molecular polarity basically are the same thing. And it's a situation where you have a diatomic molecule and it is only one bond. One bond's all you got in the whole entire thing. That is the molecule. They will be the same. When you have 3 or more atoms involved, it gets a little bit more complicated than that. And we'll talk about that in the next chapter. But this is the one place where you can do it. By the way, because this is a polar molecule, this arrow, which is the bond dipole arrow, will now become what is sometimes referred to as the dipole moment. And a polar molecule will have what is referred to as a dipole moment, which is also represented by the same arrow. And it basically points to the more negative side of the molecule and the other side that's more positive. So when you have a polar molecule as a whole, not just a polar bond, but the entire molecule is polar, there is a side to that molecule that's more positive, and there's a side that's more negative based on the overall distribution of electrons within the whole entire molecule. We'll talk more about it in the next chapter, but like something like water here. The oxygen side of water is more negative. the hydrogen side of water is more positive, and it would have a dipole moment represented by that same type of arrow heading towards the oxygen side of that molecule. But to determine if that's polar or non-polar, that molecule, it takes a lot more than just bond polarity. So that's part of it, but there's other factors you have to take into consideration when you have 3 or more atoms in a molecule.